Hello, class. Welcome to ME 391 Measurements and Instrumentation, Binghamton University. This lecture is on vibrations. It's apparent that the intensity of vibration can be measured either in terms of displacement, velocity, or acceleration. Acceleration is clearly the best parameter to measure at high frequencies. However, because displacements are large at low frequencies, it would seem that measuring either displacement or velocity would be best at low frequencies. The amplitude of vibrations can be measured by various forms of displacement transducers. Fiber optic devices are particularly attractive and can give measurement resolution as high as 1 micrometer. Unfortunately, there are considerable practical difficulties in mounting and calibrating displacement and velocity transducers, and therefore they are rarely used. Because of this, vibration is usually measured by accelerometers at all frequencies. The most common type of transducer used is the piezo accelerometer, which has a typical inaccuracy of plus or minus 2%. And as you can see here, this is a MEMS accelerometer. So we're measuring acceleration in this direction. And these are fixed plates here. And as the mass moves, it's on like little springs, so it can move back and forth due to the acceleration. The capacitance is going to change because the distance between the plate changes. The frequency response of accelerometers is particularly important in vibration measurement in view of inherently high frequency characteristics of the modern situation. The bandwidth of both potentiometer-based accelerometers and accelerometers using variable inductance type displacement transducers only goes up to 25 Hertz. Accelerometers that include either the LVDT or strain gauges can measure frequencies up to 150 Hertz. And in the latest instruments using piezo-resistive strain gauges have bandwidths up to 2 kilohertz. Finally, inclusion of a piezoelectric crystal displacement transducer yields an instrument with a bandwidth that can be as high as 7 kilohertz. As well as the accelerometer, a vibration measurement system requires other elements to translate the accelerometer output into a recorded signal, as shown here. The three other necessary elements are a signal conditioning element, a signal analyzer, and a signal recorder. The signal conditioning element amplifies the relatively weak output signal from the accelerometer and also transforms the high output impedance of the accelerometer to a lower impedance value. The signal analyzer then converts the signal into the form required for output. The output parameter may either be displacement, velocity, or acceleration. And you get this by integrating the acceleration measurement as appropriate. And this may be expressed as either the peak value, RMS value, or average absolute value. The final element of the measurement system is the signal recorder. All elements of the measurement system, and especially the signal recorder, must be chosen very carefully to avoid distortion of the vibration waveform. The bandwidth should be such that it is at least a factor of 10 better than the bandwidth of the vibration frequency components at both ends. Thus, its lowest frequency limit should be less than or equal to 0.1 times the fundamental frequency of vibration, and its upper frequency limit should be greater than or equal to 10 times the highest significant vibration frequency component. Now let's take a look at some the history of vibrations and the uses. Vibrational analysis was first used in the 1920s in California to study buildings' behaviors in earthquakes. Obviously, they wanted to improve the building resistance to damage by earthquakes. And in earthquakes, there are two kinds of waves. There are P waves, where motion is parallel to the wave motion, and S waves, the motion is perpendicular to the wave motion. And let's take a look at that here. So that's a P wave, S wave. Other applications for vibration include machinery that needs to be isolated for the comfort of building occupants. Also, telescopes need to be isolated from vibrations to ensure image quality. And also in shipping, be aware that vibrations from long trips in trucks and other transportation vehicles can be a problem, as bolts have been known to come unthreaded during shipment. And of course, the study of vibrations is critical to designing automotive suspensions. Also in aircraft, in the 1940s, many new aircraft were needed for World War II. And so the development of increasingly complex instruments and higher airspeeds drove the need to test instruments before flight certification. And the way that's done is using things called a shaker table. They are used to model vibrations and are designed for testing electronic or mechanical components. Rockets used for space vehicles and satellites undergo extreme vibrations during launch, as well as when the pyrotechnic devices detonate, for example, at stage separation. So payloads need to be designed to withstand these vibrations. Vibrational analysis and anechoic chamber development circa 1957 was used to isolate tests from external vibrations. Complex modeling techniques used in finite element analysis are also very common. I want to show you, this is Dr. Miles. He's a professor of mechanical engineering here at BU, and I want to give you a sense. He's sitting in an anechoic chamber that is in engineering science building on campus. And I want you to take a look. Here's a panoramic view. You're standing on a wire mesh, that's the floor. And all of these wedge-shaped foam-like elements. Sound goes in and just bounces around and kind of dies out. And let's take a look at some of Dr. Miles's research. It's very, very interesting.
Sound is basically, it's a propagating wave that's small fluctuations in pressure, and your ears pick up these very, very small pressure fluctuations and turn it into what you perceive as sound. I've spent a lot of the past few years designing microphones for hearing aid applications based on studies of insects. A whole lot of what you hear in any situation is really strongly affected by where you are and how reflective all the surfaces are in your room. The chamber is designed to just suck up all the sound, and it sits on springs, and so it's not directly connected to the rest of the building to keep it as quiet as possible. It's something that we spent a lot of time designing, and it met our specifications by far, and is really one of the quietest places you can go. We go into this chamber and we set up our microphone that is placed on a 5 degree of freedom robot, and we can control the position of that microphone using the computer that's on the outside of the chamber. And we can place that microphone anywhere we want inside the chamber with millimeter accuracy. And with that, through computer control, you can scan sound fields. We also have a loudspeaker where we can play out sound. Once we set it up and plug it into the patch panel on the wall, we walk out of the chamber, shut the doors, turn out the lights, and then take the data outside. This is a really tremendous opportunity for our research, and it also enables us to expand the kinds of research that we do, and it's opening up a number of new opportunities for us. Helen Keller said, when you lose your eyes, you lose your ability to see things, but when you lose sound, you lose touch with people. Sound is communication. It can help calm us down. Certainly music and the quality of sound is really important to us. At an extremely early age, I was really interested in sound. There's something about sound that really connects with me. Well, this whole project started where I was asked by some biologists to help them understand the hearing in a very, very small fly. What we ended up finding out was that this fly has eardrums. Most flies don't. And so having found that in nature, when the animal is not huge, yet it needs to tell where sound comes from, it used a certain sort of principle. By taking the ideas that we got just from the mechanical study of how these flies' ears work, we realized, that could be turned into a very tiny microphone. The truth is, discovering how the fly works was easy. Taking that idea and turning it into a working device where instead of nature doing it, now it's us. That was way harder. The device that we've been working on is intended to help people who have hearing impairment or may use hearing aids understand speech when they get into a noisy environment. There's this little dark rectangular silicon chip that actually contains the microphone itself. We put it in this aluminum box just because we don't want to get our fingers all over the microphone diaphragm. Our microphone is very directional down to much lower frequencies. At this point, we have done the research to demonstrate that the concept works. In engineering, in creating products, showing that it can be done in the laboratory is only the first step. And the next step is even harder. There are a lot of other electronic devices could benefit greatly from having a very small directional microphone. For example, your cell phone. Many students have been involved in my research from undergraduate through PhD level. And the truth is, the most important outcome from this project has been the education of all the students who have been involved in it.
It's moving right now.
Yeah. If you're an engineer, you can create things that can be very, very helpful to people. It's really rewarding to work on something that helps people a lot.
And you may be wondering why the fly needs to have such directional hearing. It's because when it needs to lay its eggs, it goes and seeks out a particular beetle and lays its eggs inside that beetle. So he needs to know where he hears the beetle's chirping coming from. So that's why the fly needs a directional hearing system. Now, vibrations can be caused by nearby traffic or subways. building mechanical systems, or just simply normal human activities such as walking across the floor. This vibration does not jeopardize the building's structural integrity, yet while the actual motion may be minimal, human perception of motion is significant, and these vibrations can be disturbing to building occupants. I don't know, some of you maybe been at some tall skyscrapers in New York City, and you can actually feel the building moving. Here's a couple of buildings being simulated during an earthquake, a couple of models of a building. Analysis of vibration modes is a critical component of design, but it's often overlooked. Structural elements such as complex steel floor systems can be particularly prone to perceptual vibration, irritating building occupants or disturbing sensitive equipment. Inherent vibration modes in structural components or mechanical support systems can shorten equipment life and cause premature or completely unanticipated failure, often resulting in hazardous situations. Detailed fatigue analysis is often required to assess the potential for failure or damage resulting from the rapid stress cycles of vibration. Vibrations can be torsional as well. Torsional vibration is angular vibration of an object, commonly a shaft, along its axis of rotation. Torsional vibration is often a concern in power transmission systems using rotating shafts or couplings where it can cause failure if not controlled.
In this module, we will discuss torsional vibration. This topic builds on many terms introduced in Module 1, namely natural frequency, resonance, and dynamic forces.
All rotating equipment, including compressors, engines, and pumps, will experience a torsional load. One important torsional load is the gas load inside a reciprocating compressor. The gas load acts on the piston and is transmitted to the crankshaft. This chart illustrates the gas load from all the cylinders during one revolution of the crankshaft. Another important load is the inertial load due to the weight of the piston assembly. Inertial load for all cylinders also varies widely over each revolution. By adding together the gas load and the inertial load, we find the combined torsional load for all cylinders in this compressor. The load from each cylinder acts on the crankshaft, resulting in a torque that can cause vibration problems. Each machine will have a unique load profile. A torsional vibration analysis considers how this combined load interacts with the crankshaft, the engine or motor, the coupling, and the resulting stress and vibration on the system. A complete drivetrain or torsional system, for example, a reciprocating compressor with a coupling and an electric motor, has a torsional natural frequency, or TNF.
Torsional natural frequency is defined as the frequency at which a shaft twists back and forth. Imagine twisting a shaft by rotating one end. After releasing the shaft, it rotates back and forth. This oscillation occurs at the torsional natural frequency. This is analogous to the mechanical natural frequency described in Module 1. Torsional vibration can occur, especially if the system is resonant. In this example, the vibrations are low at 900 RPM. As the speed increases, the system becomes resonant at 1200 RPM when the speed is at the TNF.
At resonance, the vibration response is greatly amplified. Above the resonant frequency, vibration response is significantly reduced. The torsional analysis must accurately predict resonant conditions and vibration problems. If not, the results can be catastrophic.
Destroyed couplings, broken compressor shafts, broken motor shafts, not to mention the downtime and cost if the unit is inoperable for 1 to 2 months.
Torsional vibration is often called the silent killer because a failure like this occurs without warning. The best way to mitigate these failures is to order a torsional vibration analysis before a unit is built. With early involvement, the system can be modified more cost-effectively and easily than later. Changing the coupling size or style, adding a flywheel or a detuner, and changing the shaft material or size are all easily done if the components haven't been built. If the system is already built, then needed modifications are often more expensive and complicated, resulting in delayed delivery of the unit. The next time you are involved with ordering or designing a rotating system, it is highly recommended that you have a torsional analysis performed. This module is a brief introduction on torsional vibration analysis. The key points are that torsional vibration can result in failure.
A torsional vibration analysis should be performed very early in the package design phase.
The analysis should adequately cover the entire operating condition envelope, including upset conditions, while addressing tolerances in manufacturing and installation. For superior accuracy and practical recommendations, please contact Beta for your next compressor or pump project.
This module is a short refresher on key topics on vibration relating to reciprocating compressors. These include locating and measuring vibration, relating vibration, stress, and failure, and the vibration equation. Vibration can occur in many different parts of a compressor package. Depending on the root cause, vibration is often found in the bottles, the scrubbers, the frame, the piping, and the foundation. This animation illustrates how the pipes, scrubbers, and bottles will typically vibrate. Our machine analysts need to understand the location and magnitude of vibration in order to develop the best solution. In addition to the main piping and compressor components, we see a lot of vibration problems due to small diameter piping used for sight glasses, floats, thermowells, and other instrumentation lines. These lines can easily vibrate, crack, and even cause gas releases. Excessive vibration leads to high stress levels on machines and other related components, which leads to fatigue failure. Here are some prime examples of fatigue failure: cracked pipes, nozzles, or scrubbers, failed clamps and bolts, broken crankshafts, compressor station fire, and poor foundation installation. Damaged components lead to costly unplanned shutdowns which can last for days or even months, depending on the extent of the problem. Parts replacement such as crankshafts or pulsation bottles can take several weeks to obtain, and the associated repair and downtime costs can run into the hundreds of thousands of dollars. In fact, a number of recent failures resulted in downtime costs exceeding the $500,000 mark. We also encounter situations where significant collateral damage occurs as a result of equipment failure. This photo shows a cracked component which released gas that resulted in a fire. Left unattended, a vibration problem can become a serious safety hazard with equally serious financial consequences. Luckily, there are many proven solutions which address these issues, but owners and EPCs must specifically ask to have pulsation and vibration studies included with their order for a new or revamped compressor. To fully grasp the concept of vibration, one must understand its mechanics. The amount of vibration is defined by dynamic force and dynamic flexibility. Dynamic force is created by the combined motion of the piston, crankshaft, and other moving parts of the engine or compressor. The force is described as dynamic because it continuously changes in the course of each cycle. The dynamic force can be shown in a frequency diagram. The magnitude of force will vary with frequency. Dynamic flexibility is the other factor in the vibration equation. Dynamic flexibility refers to the flexibility at different frequencies. A support might be stiff at one frequency and be very flexible at another. The frequency at which a structure attains its flexibility is referred to as its mechanical natural frequency, or MNF. Every system will have at least one MNF. It can have several. We'll see some examples in a moment. Resonance is an important term related to MNFs. A system is said to achieve resonance when a force occurs at the mechanical natural frequency. At resonance, the effect of a force is typically amplified by 20 to 50 times, creating excessive vibration. This explains why some structures fail. Here's a simple example to show the relationship between resonance, MNF, and dynamic force. So I'm going to tap the ruler at a frequency well below the mechanical natural frequency. So a small vibration will result. If I tap the ruler faster, closer to the mechanical natural frequency, the amplitude of the vibration starts to get very large. If I tap it much faster than the mechanical natural frequency, again, there'll be some vibration, but nothing like at the mechanical natural frequency. You can see that the steel ruler is very flexible at this specific frequency and location. This is the ruler's MNF. Here's another example. This scrubber is stiff at low frequencies, but is more flexible at higher frequencies. This illustrates the mechanical natural frequencies where the pipe has low stiffness. If there is a force at this MNF, then the scrubber starts to resonate. The designer must be careful to avoid resonance on all the individual equipment components because even small forces can create shaking problems that result in failed components. For new and revamped compression packages, Beta identifies the forces and mechanical natural frequencies of the system. By working with the customer, we find the optimal design that reduces forces on the package and adds sufficient stiffness to ensure a reliable installation throughout various operating conditions and load steps. Let's summarize this module. To develop the best solutions, Beta's analysts identify the location and magnitude of vibration. Excessive vibration leads to high stress levels on machines and other related components, which leads to fatigue failure. The amount of vibration is determined by two factors: dynamic force, created by the combined motion of a system's moving parts, and dynamic flexibility, which is a system's ability to withstand reciprocating forces. Vibration is mitigated by either reducing dynamic forces, reducing dynamic flexibility in the support structures, or both. And lastly, a system is said to achieve resonance when a dynamic force occurs at its mechanical natural frequency. In the context of system integrity, this is a critical state where forces are often magnified from 20 to 50 times and which often leads to structural failure. In this module, we'll be looking more closely at the sources and magnitude of forces which cause vibration problems and see how pulsations are generated within the system. Now let's look at the reciprocating compressor in more detail and identify the key forces acting on pipes, vessels, and foundation. Pressure pulsations. Pulsations are created as gas enters or leaves a cylinder in short bursts. Pressure pulsations travel through the piping and vessels. Pressure can create very high unbalanced forces between 10 and 10,000 pounds peak to peak. Mass unbalance. Because it is virtually impossible to create a system where the mass of all the different components are perfectly balanced or distributed, these imbalances translate to vibrational forces when the system is set in motion. Moment or couple is referred to as the magnitude of force applied to a rotational system at a distance from the axis of rotation. In a reciprocating system, this couple is generated between throws around the vertical axis of the compressor. Cylinder assembly stretching force results from force transferred to the cylinder by the pressure generated by compression resulting from the motion of the piston. This is also referred to as cylinder stretch or gas forces. Crosshead forces. As the rotating motion of the crankshaft gets converted into the reciprocating motion of the piston, a residual vertical force is created at the crosshead. Misalignment generates an unwanted radial and/or axial force on the compressor and engine, a force which is magnified at higher speeds. Now that we've defined the 6 types of forces, we can look at their total impact on a compressor package. This chart shows the magnitude of the force at the fundamental frequency, or 1 times run speed. There are also forces at higher multiples of run speed, such as 2 times, 3 times, and so on. These higher order forces are also called harmonics. Pulsation forces and cylinder stretching forces are examples of forces that occur throughout every multiple of run speed. So you can see that forces on the compressor occur across a wide range of frequencies. These dynamic forces generate vibration as defined in the vibration equation. Vibration equals dynamic forces multiplied by dynamic flexibility. Pulsations are pressure waves created during the reciprocating motion of a compressor piston. Here's a simple example. As a piston moves forward, it pushes the gas or fluid ahead of it, which increases the pressure at the face of the piston. This creates a high pressure area that propagates at the speed of sound throughout the system. This animation illustrates the formation of pulsations. Like a ripple in a pond, the waves continue to travel away from the source, except with pulsations, they travel at the speed of sound in the fluid. As the piston returns, an area of low pressure forms behind the piston. This low pressure also travels away from the piston at the speed of sound. Pulsations exist in the suction and the discharge systems. They travel through the bottles, the piping, off to the cooler, and then through the off-skid piping. Each wave can be greatly amplified due to a phenomenon called acoustical resonance. Here's a very simplified example of acoustic resonance. Let's follow the progress of a pulsation wave as it travels along a pipe and through an open leg or vessel. The yellow wave indicates moderate pressure amplitude. The wave is traveling at the speed of sound. As the wave enters the opening, a small wave is reflected backwards. Green indicates a very low amplitude wave. Note the original wave gets a bit smaller. Now the wave exits the chamber or opening. Due to the change in area, a small wave reflects off the edge and travels backwards as shown in green. The original wave is further reduced as it continues through the pipe. Note there is still a remnant of the initial wave reflecting in the space. The next wave enters and the process repeats, including the small reflected waves. Depending on the geometry, frequency, and other factors in the system, the two other waves may be in phase. If the waves are aligned, then the amplitudes will add. The process repeats with each stroke of the compressor. Now the reflecting waves are in phase with the main wave, and the maximum has been reached. This is called acoustical resonance, because the reflections are in phase with the primary pulse. The pressure wave can be amplified significantly, even up to 50 times higher than the original wave. If this acoustical resonance happens, then violent shaking and pipe failure are likely to occur. Now that we understand how pulsations are created and amplified, let's look at how they create shaking forces in the piping system. For this example, the average pressure is 1,000 psi. The amplitude of these pressure pulsations can vary widely. Let's assume no pulsation control exists and the pulsation levels can reach a relatively low amplitude of 6% peak to peak. The maximum is 1,030 psi and the minimum is 970. The differential pressure equals 60 psi between maximum and minimum amplitudes. As the wave travels through the pipe system, an unbalanced force is created at T's, elbows, and locations where the pipe changes size. The force equals pressure times area. Using the same pressure pulsation, the differential pressure is 60 psi. The maximum force will occur when the maximum pressure occurs at one end and a minimum pressure occurs at the other end. The area the differential pressure acts against is the projected area of the pipe on the elbow. For this 6-inch pipe, the area is about 28 square inches. As the pressure wave travels 180 degrees, the differential pressure reverses direction and is now minus 60 psi. The unbalanced force is now 1,680 pounds in the reverse direction. The force oscillates back and forth at the run speed. For a 1200 RPM machine, the frequency is 20 times per second. This means the unbalanced force of over 1,600 pounds is shaking back and forth at 20 times a second. This puts extreme stress on clamps, bolts, and sleepers, trying to hold the pipe in place. Forces from pulsations can range from less than 10 pounds to over 10,000 pounds. Here is an example to illustrate pressure pulsations in an interstage system, from discharge through the cooler and back to suction for the next stage. The pulsations are indicated by color pressure points. Yellow represents positive pressures, and 180 degrees later the pressure is reversed as shown in blue. These pressure pulsations are occurring at many times per second. Plane wave theory is used to predict these pressure standing waves. Using our unique software tools, we can assess the pulsations throughout the package and for every different operating condition. Knowing the geometries, we can convert the dynamic pressure changes to unbalanced forces. The red vectors are forces, and the arrows indicate the direction of force. The length of the vector represents the magnitude of force at the specific location. You can see that in some areas these forces are excessive and must be controlled. We then evaluate the system and offer recommendations to ensure these unbalanced pulsation forces are controlled and under guideline. For modeling pulsations, we recommend using time domain analysis. This type of algorithm is more accurate than the older approach that uses frequency domain analysis. Beta pioneered time domain analysis in the 1990s and employs this technique on all pulsation studies. This chart shows the frequencies where the pulsation forces exceed guideline. Notice that the frequency domain model predicts high unbalanced forces at 160 Hz. Using this approach would likely result in higher cost pulsation bottles. When using the more accurate time domain approach, notice the prediction is much lower, and in this case it is close to the guideline. The improved accuracy of time domain offers advantages such as more cost-effective pulsation bottles, a significant savings which can be more than the cost of the study. This proprietary software tool is more accurate at high frequencies. While time domain is widely accepted, it should be noted that many firms do not have this capability. A few moments ago, we looked at pulsation forces at one operating condition. However, most compressors operate at many different conditions based on different operating pressures, flow rates, and loading configurations. Pulsation forces will be different at each condition. This chart illustrates the importance of analyzing all operating conditions. This compressor has 31 different conditions. At 1 times run speed, there are many conditions where the forces exceed guideline. We also have to catch problems at higher frequencies. In this case, we see some conditions where forces exceed guideline at 4 times and 5 times run speed. Understanding and addressing problems at specific run speeds will avoid failures or operating problems. Beta and other leading machinery consultants strongly recommend evaluating all operating conditions. Shortcuts that examine only a few cases will often produce disastrous results. For variable speed drive and mini engine applications, the analysis should evaluate the system under the entire speed range. For fixed speed motors, it is important to look at plus or minus 10% around the planned speed. Let's summarize this module. There are many forces generated by a reciprocating compressor package. This module describes how pressure pulsations are created during each cycle of a piston. Key points are: pulsations are pressure waves that travel through the system. At resonant conditions, pulsations are added together to create very high pressure fluctuations. Unless controlled, pulsations create damaging forces on the piping system. The unbalanced force equals pressure times area. Unbalanced forces must be identified throughout the package, including off-skid piping. Beta's role is to design a pulsation control solution that reduces pulsations to acceptable levels on new systems or revamps. When doing a pulsation study, it is important to check all operating conditions for pulsations, including the adequate speed range for fixed and variable speed applications. Time domain modeling techniques should be used for improved accuracy over the older frequency domain approaches. The remaining forces on a reciprocating compressor cannot be eliminated. They are inherent in the reciprocating motion, so the design must accommodate the forces without failure. This is part of the mechanical design undertaken by Beta and discussed in later modules.
Now, in this table, the first and second here you can see different types of modes in the cantilever beam. There's the first mode in horizontal, and in the second mode horizontal, you can kind of see there's 2 nodes going on there. And in the torsional, you can see torsional vibration here and a multi-node second mode here. And then in the other direction, it can be compressed. You can also get multimodal vibrations there. A 2-dimensional elastic membrane under tension can support transverse vibrations. The properties of an idealized drumhead can be modeled by the vibrations of a circular membrane of uniform thickness attached to a rigid frame, as you can see here. Due to the phenomenon of resonance at certain vibration frequencies, its resonant frequencies, the membrane can store vibrational energy, the surface moving in a characteristic pattern of standing waves. This is called a normal mode. A membrane has an infinite number of these normal modes, starting with the lowest frequency, called the fundamental node.
Here's the lowest frequency vibrational pattern in a circular membrane. This circular membrane is a piece of dentist rubber dam. It's stretched over a short length of PVC pipe and held in place with some rubber bands. And this lowest pattern, the entire membrane moves up and down together as one piece. The whole thing moves together. Here's the second pattern for the same membrane. Occurs at a little bit higher frequency. Half of the membrane moves up while the other half is moving down, and there's a line right across the diameter called a node that doesn't vibrate at all. Here's the third pattern. The membrane, there are two sections. Actually, it's kind of like a cloverleaf pattern. Two opposite sides of the membrane move up together, and the adjacent sections move down. So there's four regions that move alternating up and down. Here's the fourth pattern. The center of the membrane moves opposite the outside edge. In fact, there's a circle that doesn't move at all. This is a pattern where the center and the outside edge move in opposite directions.
A non-Newtonian fluid is a fluid that does not follow Newton's law of viscosity. Most commonly, the viscosity, which is the gradual deformation by shear or tensile stresses of non-Newtonian fluids, is dependent upon the shear rate or the shear rate history. Let's take a look at this video. This is a non-Newtonian fluid. It's cornstarch and water mixture, and it's on top of a speaker, and we're going to see the different reflections, the different waveforms as the frequency, the vibrations changes. So the frequency is gradually being increased. There's also wind loading on buildings, as you can see in this animated GIF. Especially in New York City, in those tall skyscrapers, the wind ripping around, and you've got to be very cognizant of the wind loading in those tall buildings. This is a way to prevent vibrations during earthquakes. It's called a tuned spring mass damper system. This particular one we're seeing is hung between the 92nd and 88th floor of Taipei 101, 600 metric tons and 5.5 meters in diameter. Let's take a look at this.
The threat of tropical storms hangs over Taipei 101. It's not fear of collapse, but a delicate issue of customer comfort. The typhoons that blast through the city of Taipei mean driving rain and 160-kilometer-an-hour winds slam against Taipei 101, and it feels it.
You see, a tall building like this is prone to bend in the wind. Remember the bamboo, flexibility and all that. Now, some flexibility in a tall building is a good thing, and it's difficult to avoid. But too much, and it can give the people inside it motion sickness. When I asked the engineers what a typhoon might feel like in a tall building, they said, try eating soup on a bus. So I did.
Before Taipei 101 was built, it had to overcome the problem all flexible buildings face, swaying back and forth in high winds.
And like any structure, it has a natural frequency. And in this case, one complete cycle of swaying motion from here to here and back again takes about 7 seconds. Now, for customers in the restaurant, that would be like sitting on board a bus that every 3.5 seconds accelerates and then brakes. And that's the delicate problem I'm talking about. At the top of the Taipei Tower in a typhoon, you wouldn't just spill your soup, you'd probably see your whole lunch again.
The building's accelerations or movements can be plotted. This is uncomfortable. The designers of Taipei 101 must slow down the acceleration and deceleration, smoothing the rate of change to avoid motion sickness.
But how on earth do you stop a building over 0.5 kilometre high from picking up a nauseating sway in strong winds? This is how. The world's largest and heaviest damper, suspended between the 92nd and 87th floors on 16 huge steel cables.
Heavier than 3 jumbo jets, the giant ball will swing like a pendulum. The swinging counteracts the building's sway. It uses a property that all objects have.
It's called inertia.
If something is stationary, it wants to stay still. If it's moving, it wants to carry on. The desire of an object to keep doing what it's doing is inertia at work. Back in the 1950s, a researcher at Cornell University encountered the destructive side of inertia. His name was Hugh de Haven. After surviving a serious air crash, de Haven was motivated to study collisions. As surprising as it may sound today, back then, the common belief was that you were better off being thrown free in a car crash. De Haven realized the damage was done as passengers fly loose and impact their surroundings, and that inertia was the culprit. But restraining them would protect them. In 1951, Hugh de Haven files a patent for the 3-point seatbelt, and car passenger safety leaps forwards. 2 decades later, the inertia reel safety belt is introduced, initially by Volvo and Ford. It leaves you free to move around, only locking under sudden movements. It uses the very same property of inertia that Hugh de Haven realized caused injury. Inside an inertia seatbelt sits a heavy steel ball. When a car is in a collision, the inertia of the ball means it will move independently. The moving ball hits an arm that pushes up and triggers a process that locks the belt. Inertia is also harnessed in the giant 600-ton steel ball suspended at the top of Taipei 101. When the building sways, it swings like a giant pendulum. It then pushes against oil-filled shock absorbers or dampers that dissipate the sway. I want to check out the damper for myself, so I have permission to go into a construction area underneath it. It feels a bit like caving, except I'm in a tunnel over 80 stories up.
Wow! Here it is, the heart of it.
6 meters in diameter and made up of 41 separate steel plates. Only now do I get a sense of what a radical and inspired idea it is.
Suddenly, now I see it, I understand much better about how it works. This massive ball, this weight, sits here in the middle of the building, and as the building starts to move, at first the ball resists that movement. Then it starts to move, but that's where these come into play, and they're kind of like the shock absorbers on your car, only massive. And as the ball moves, these absorb the energy, they soak it up. And all of this is happening. Hundreds of tons of steel swinging about, 80, 90 stories up.
C.P. Wang, the architect of Taipei 101, has his own demo of the damper at work. So I went to meet him at the top of his award-winning building.
When wind hits the building really moves.
Yeah.
And it starts doing all that for a long time. It makes people uncomfortable working in the building. So what we have designed is this. If you would please take that down.
Okay. And this is more...
Replace this with this. Yeah, the purpose
This
is
has
to
got a
make it
ball
the same.
in
Yeah.
it.
This is our damper, actually the heart of the building.
Wang explains his metal ball in this demonstration is in an oil-filled tube. This best represents the oil-filled shock absorbers attached to the giant damper.
Okay,
if
so
you
I'll
would
mount
put
that
that
in
in.
So this is now with your damper in.
Now the wind is blowing again, and
Wow. So it doesn't stop it moving, but once it started moving, it takes the violence out of the movement. It doesn't accelerate or slow down as quickly. It's a more gentle feeling. I suppose what it's doing is giving you a better ride up here, isn't it?
buildings are for people to use. So if we cannot make the people comfortable, we don't have a good building.
On the 3rd of October 2005, Typhoon Long Wang blasts hurricane-force winds across Taiwan and presents the damper system with its first serious test. This film shows the ball in action as the 110 km/h winds blow that day. As it begins to swing, the giant oil-filled cylinders take up the energy from 500 tons of swinging steel. This extraordinary footage, filmed on a cell phone, reveals the ball damping 545,000 tons of skyscraper as she sways in the typhoon. After 3 hours, the winds abate, leaving Taipei 101 to face another day.
Here's another one animated GIF. This spring mass damper is in Hancock Tower in Boston, Massachusetts. So it's very similar to the one that you just saw. And we've already seen this in a previous video, so we'll just move on. This one's interesting. This is the rebuilt bridge in San Francisco after the earthquake.
The new eastern span of the San Francisco-Oakland Bay Bridge, which is due to open next year, is designed to survive a strong earthquake along either of two nearby faults. This earthquake simulation shows the kind of movement that would be experienced on the span's 1.2-mile-long elevated roadway, called the Skyway, and on its suspension bridge, which is about a half-mile long. Where the bridge and Skyway meet, and at other joints along the span, 60-foot-long steel connecting pipes would allow movement during a quake. A section of weaker steel in the middle would act like a fuse, absorbing much of the energy to spare the rest of the structure. On the suspension bridge, the tower and roadways would move independently. The tower's 4 shafts would sway up to about 5 feet, but damage would be confined to steel connecting plates called shear links. The bottom of San Francisco Bay is covered in deep mud, which can amplify ground motion in an earthquake, so piles for the span's piers were driven at an angle to provide more stability. If the design works as planned, damage from a major quake would be limited to a few parts of the span, and the bridge would be reopened to emergency vehicles within hours. This is Henry Fountain of the New York Times.
So let's take a look at the spring mass damper system. You may have seen this before in physics. The resistive force is equal to the K times X, which is the force due to the spring. You can visualize this damper as a fluid-filled cylinder piston with holes in the piston. And the resistive force from the damper is given by c times x dot, so the velocity of the mass. And here is the equation. This is Newton's equation, of course. So we come up with this second-order differential equation here. And the solution to this is given here. You don't need to know this, but it is basically a decaying cosine wave. Now I'm going to define some terms here that you're going to actually be doing this in the lab. So this is important. So logarithmic decrement is used to characterize the rate of the decay. And it's defined by this equation here. The logarithmic decrement delta is equal to 1 over n times the log of x naught over xn, where x naught is the amplitude of the first wave, and xn is the amplitude of some wave n. And n is the wave number. So you can see that here, 1, 2, 3, and 4. It's best that you try to get n to be as large as possible. Maybe in this case you could read the amplitude of the wave here and use n is equal to 4. So that characterizes the rate of decay. And then we have something called the damping ratio. It's defined as the ratio of the damping coefficient C due to the critical damping coefficient C sub C. Now C sub C occurs when psi is equal to 1, the logarithmic decrement, the damping ratio rather. So the damping ratio is defined by this equation here. C sub C occurs when the damping ratio is equal to 1, and that's called the critical damping ratio, and that's very important because you want a system that has as little oscillation as possible. And if you know, so critical damping, let's re-describe that. So let's say you have a car suspension and it gets displaced. Well, the ideal damping ratio would result in the suspension returning to its original position as fast as possible, and that's called the critical damping ratio. And if the damping ratio of the system is equal to the critical damping ratio, the damping ratio is equal to 1. The critical damping rate coefficient, sorry. And if you know delta, you can calculate what the damping ratio is. And if you know the damping ratio, you can calculate delta. Let's take a little bit closer look at the damping ratio. The blue line is when the damping ratio is less than 1, so the system is displaced, and then it overshoots a little bit, and then it comes back a little bit, and then it does eventually damp out the vibration. The ideal is a damping ratio of 1, and that's the green line, where the displacement returns to 0 without any overshoot. And if the damping ratio is greater than 1, that's the red line. It just takes it doesn't have any oscillation, but it just takes a long time to return to 0. And if the damping ratio is 0, of course, you have no damping at all. Now, these are the undamped natural frequency. So of a system, when you don't have a damper, the undamped natural frequency is given by the square root of k over m, where k is the spring constant, m is the mass. But if you do have a damper, the damped natural frequency is equal to the undamped natural frequency times 1 minus the damping ratio squared. And if you have the frequency, you can turn that into omega. Omega is radians per second, and the frequency is in hertz, so just multiply by 2 pi. The damping coefficient is given by this equation here, 2 times the mass times the damping ratio times the undamped natural frequency. And the critical damping coefficient can be calculated using this equation, 2 times the square root of Km. And here's the vibration experiment. We have a cantilevered beam. We have an axial strain gauge mounted on it. We have a DC motor. It has a plastic disc attached to the shaft with an eccentric weight on that disc. So as the motor turns, it will produce a force on the end of the beam. And be very careful with this experiment because the beam's going to be bouncing around. We're actually going to clamp the system to the workbench top. So as the driving frequency, that is the DC motor, changes revolutions per second, it'll eventually approach the beam's natural frequency and the beam displacement will grow. And we're going to measure the beam displacement by measuring the actual strain on the system. So as it oscillates up and down, we'll be able to read the strain gauge, which will also change strain in accordance with the motion of the beam. And if you plot the displacement versus the driving frequency, you can calculate the resonant frequency of the beam. Okay, that's it. Good luck in the lab. See you in cyberspace.